Okay, so let me start. So just briefly recall one of the results that we proved last time. That was the following. Suppose you have a function f defined on a closed bounded interval and which is continuous. Then if you look at the infimum of the range of f, and if you look at the supremum of the same, then both these numbers are attained somewhere. So let's say the infimum is m, then there is a point c where fc is equal to m, and there is a point d in the same interval where fd is equal to m. So both are attained. So another way to express this would be to say that f has a maxima and a minima on. Okay, so this is the meaning is the same as this, that there exists c d in this interval such that fc equal to small m and fd equal to capital M. And so what was the proof? So roughly the proof went as follows. So let's say we are talking about small m, then so this is infimum of the range. So first you get a sequence here in this set which goes to small m. So any sequence here in the range would look like this. So you get hold of a sequence that goes to small m. Next you look at the sequence xn. All these xn's, they are in this closed bounded interval, so admits a convergent subsequence xkn, which is to say that xkn converges to some x belonging to this same interval. And now use continuity. Use continuity of f at x. So what that gives you is that f xkn would go to fx, but by your choice, the fxn sequence to begin with was converging to m, so this subsequence will also converge to m, and these two together would tell you that these two numbers have to be the same. So that was the argument here.
So we first have to prove that infimum exists also, right? Like we cannot straight away go to this step.
Yes, that is true. So how did we do that?
We assume that it did not exist, and then we showed that continuity will be bounded.
Right. So essentially same argument. If the set is not bounded below, then you get hold of a sequence that goes to minus infinity, and this part of the argument remains the same. And then you try to use continuity, so you arrive at exactly this step. But here what would happen is this would go to minus infinity, whereas this is supposed to go to this specific value. That gives you a contradiction if it is not bounded below, right? Yes?
Yes.
Yeah. So both parts, the argument is very similar. So the first part, yes, I forgot to mention that. So first part, you show that it is not bounded below. So in which case you get hold of a sequence that goes to minus infinity. This part of the argument remains exactly the same. You get look at this sequence xn. This xn sequence would come from this bounded interval, closed interval a to b. It admits a convergent subsequence that converges to something in the same interval. Now you use continuity of f at this point x. So since xkn goes to x, fxkn by continuity has to go to fx, but fxkn is going to minus infinity now in the first part of the proof. So this would go to minus infinity. So you get equality, which gives you a contradiction. So that tells you that the range is bounded below, and then the infimum is a real, and that is attained. For that, again, you repeat essentially the same argument. Okay. For maximum, the proof is exactly similar. Now, why I'm repeating this? Now, suppose your function f to begin with is defined not on a closed bounded interval, but on a closed bounded subset of R. Okay, so you're not insisting that this should be an interval. Now you look at this argument and see if it still goes through. So first part of the argument, if let's say it is not bounded below, which means if m is minus infinity, so you carry out this, try to follow the exact same path. So where did we use the fact that it's defined on a closed bounded interval? It is here that xn admits a convergent subsequence. Now, what happens if you have a closed bounded set instead? So why does this sequence admit a convergent subsequence? First of all, this is a bounded sequence because it comes from this closed bounded interval. But it would be a bounded in sequence even here when the terms come from E. So if all the terms are from this set E, which is closed, and for this part, what is important is bounded, then xn is bounded. And then we know that it admits a convergent subsequence in R. So the next point is that the limit, whether there is a subsequence that converges to something. So the next point is that this limit should belong to E. And why is it so? Because E is closed. You have a sequence now in E which goes to a limit. So that limit has to be in E. So this closeness gives you that. So that AB was an interval is not important. What is important is that it is closed and bounded. So the entire proof would go through. So I'm not repeating. You can just look at the proof in the earlier case and just check that everything goes through in this case also. So then you can have a stronger version of that result, namely that if or rather E is a closed bounded subset of R, if E to R is continuous, then if
Sir, I have a question.
Yeah.
So 0 to 1 close interval union 2 to 3 close interval is a closed subset and
closed
bounded.
bounded subset.
So
Yes.
how do we define continuity on this?
Yeah. So the points where you have doubt would be 0, 1, 2, 3, right?
Yeah.
So now, okay. So now let's just go back to the definition of continuity at a point. So this is continuity at A, right?
Yes, sir.
And by definition, you say that if is continuous on a set E, if F is continuous at A for all A in E. Now, so here, that means you have to have continuity at all A's here in this interval and all A in this interval, because the union is your set E. Okay. Now you don't have any doubt about points here. If A is in the interior, let's say A is in this open interval, because then you already can talk about the limit here, and only points of concern are values of F in a small neighborhood, which is entirely contained. For the endpoints, so let's say at 1, continuity at 1. So continuity at 1 here would mean this.
Okay. And at
Okay.
2 it will be 2 plus.
Yes, yes. And similarly at 0 it would be 0 plus, right hand limit at 0. At 3 it would be left hand limit at 3.
Yeah, okay, sir.
Okay, so actually if you recall, when I defined limit, I had just remarked and I said that we won't we would define only for limit only for the case where F is defined in a deleted neighborhood of A. But at that time I had remarked that what you need is in order to define this quantity, F should be defined on a set E, and A should be a limit point of E. Okay, in such a situation, you can define the limit of a function as x goes to A. That is something I had just commented, but what I actually wrote down, it was in terms of deleted neighborhood and so on. But now all of those things you can carry out in this situation also. So you have to just appropriately modify. Let's say if is defined on E and A is a limit point of E, then you say that this is this if given any epsilon positive, there is a delta positive such that okay, so the next part you have to just make a slight modification. So normally this next part was that whenever x belongs to A minus delta to A plus delta minus the point A itself, you should have fx minus fa less than epsilon. So here what you do is now, so this set need not be in the domain anymore, because you have not assumed that f is defined in a deleted neighborhood of A. So this intersection E. You have to make this slight modification. Okay, so which translates to when such sets are involved, like the set in your example, it would boil down to a left limit somewhere, a right limit somewhere else. But the situation can be more general, and there also you can talk about continuity limit, etc.
Okay, sir.
Okay. So yeah, so the earlier result on closed bounded interval, that can be generalized to a closed bounded subset of R. Okay. So another just remark I'll make, I won't get into the details. So in general, such a statement, that is, F is defined on a subset of R continuous, and F attains or F has a maxima and a minima. So this is the general nature of the statement, and we had just imposed a condition that E is closed bounded. So here, the more general, I should not say more general. Okay, let me just say what I want to say. So if E is, so this is something I have not defined, but you would have, at least some of you or most of you would have encountered this compact set. So this statement remains valid whenever F is defined on a compact subset of R. Okay. Now, compact set, how are they defined? In a topological space, that is, if you recall, set equipped with a collection of subsets satisfying some properties closed under arbitrary union and finite intersection, etc., and contains the empty set and the entire set. So there it is defined in a certain way. Maybe I'll just mention the definition. You don't have to worry about it for this course or this exam, but so I'll write down this definition in a moment. Now it turns out that for R, for subsets of R, whatever this description is, that becomes equivalent to saying that is closed and bounded. Okay. So in other words, what I'm saying is, maybe I hope I'm not making it too confusing. So again, this is something I had remarked last time. Suppose you are defining a function from X to R, where X is a topological space. Okay, so I had mentioned that you can define continuity in this setup also. The way to define that is that inverse images of open sets are open. That is how one defines a continuous function from a general topological space to R or another topological space, where you don't have the notion of a distance necessarily. Okay, so now, So you can define continuous function in this setup. Now suppose you have this situation where this is a general topological space, but on the right side is R. Okay, here if F is defined on a compact subset of X, then F has a maxima and a minima. And when you specialize to R, subsets of R that are compact are exactly this class of sets, that is closed and bounded sets. Okay, now what is a compact set? So let's say you have X, you have this subset K. Okay, so I have to give one or two more definitions, but this is just, I mean, after this page, you can forget about it if you want to. So you say that a collection of open subsets is called open cover for K if so these are U alphas. So you would call this collection an open cover for this set K if their union covers K. Okay, so the term cover is for this inclusion, and this term refers to the fact that each U alpha is open, each member is open. So such a collection of subsets is called an open cover. Okay, now what is a subcover? So suppose you have it's like this. Let's say you have this set K, and let me use another color. So let's say you have U1, U2, U3, U4, U5, U6, U7, and then let's say U8. So K is, this collection need not be finite, but just for this example, so that I can draw everything, taking this collection to be finite. So this collection U1 to U8, that gives you an open cover for K, or cover for K. Okay. Now, if you look at this picture, you can safely take out U8. So this is also contained in 1 to 7. So in this case, U1 to U7, that's a subcover of U1 to U8, and cover, subcover, etc., everything for the set K. So there has to be a set K about which you are discussing. So this is the notion of subcover. So if there is a smaller collection that also covers the set, then you call it a subcover. So what is a compact set? K is said to be compact if every open cover for K has a finite subcover. Okay, just as an example, so let's say let's go to the real line with which we are familiar. Let's take the set K to be 0, 1. Okay, now my claim is that this is not compact, which means that I can produce an open cover which does not have a finite subcollection that still covers this set. So for that, you can take, let's say, U1 to be half to 2, U2 to be 1/3 to 2. So basically something like this, half to 2, 1/3 to 2, 1/4 to 2, and so on. So if you look at these events, zero, 1 is contained in okay. Now, if you take a finite subcollection, then you can see from the diagram you can see, but you have to write down a precise argument. As soon as you have finitely many of the events, what would happen is that you'd come down to some 1 over n, and then the points here, those would be outside the union. So the union will not cover the entire set. Okay, so this is an example of a set which is not compact. So this is the definition of a compact set. And going back, for subsets of R, being a compact set and being a closed and bounded set, they're equivalent. Okay, so I won't get into compact sets. I won't get into anymore. I just wanted to make this remark. This is, some statements are actually part of the official syllabus, but again, I have had to skip a few things, and those won't be part of your syllabus for the final exam. But those of you who plan to pursue or think you are going to need analysis later also, you should read a little bit, maybe after the exam, about this. Okay, so last time I think where I stopped was I just mentioned uniform continuity. So uniform continuity, I said, is when the choice of delta depends only on epsilon but not on the specific point. So you say that F is uniformly continuous on, again, I'm defining it just for simplicity. On an interval, it could be any set where F is defined on a set E, and you can define this notion on that set. continuous on if given any epsilon positive, there is a delta positive such that so there's no base point specified here. There's no no fixed point that has appeared yet. Just you are given an epsilon positive and there's a choice of delta corresponding to this epsilon such that whenever you have 2 points xy belongs to AB or E and x minus y, they are at a distance delta apart, the corresponding f values are at most epsilon apart. Okay, so there's slight difference from the definition of continuity at a point. When you discuss continuity at a point, so this is uniformly continuous, and continuity at a point A, then along with this epsilon, you also have maybe I should not write A because I have used A here, continuity at a point C. So along with epsilon positive, you are also given C in the set where F is defined, and then what appears here, the definition of continuity at C is that x minus C less than delta, and x belongs to E. While here you are just taking any 2 points x and y which are at a distance delta apart. So that's the difference. Okay, now one of the properties that we proved last time was so what did that theorem tell us? That told us the following: if f is defined on a closed bounded interval and it is continuous, then given epsilon positive, there is a partition such that the oscillation over each subinterval is at most epsilon, is less than epsilon. So which is to say that this is less than epsilon for all each I. For each subinterval, this happens. So this was a small span theorem. Now suppose you choose your partition corresponding to, let's say, not epsilon, but epsilon by 2. So that same theorem would give you a partition corresponding to epsilon by 2 also. That's not a problem. Okay. Now, now you look at these distances. So xi plus 1 minus xi. So these are all positive, right? I equal to 1 to n minus 1. So we look at the minimum of these distances. Call it delta. So this is going to be positive. These are all positive, finitely many quantities, their minimum, so it's positive. Okay, now let's say you take two arbitrary points in this interval, not completely arbitrary, which are within delta distance of each other. Now, then in terms of this partition, what can you say about x and y? Let's say
if they belong to the same partition, then it's less than epsilon.
no, fx will come to later, but just position of x and y. What can you say from this? That if we know that they are within delta of each other, then
they're like the distance between them is less than the sum of two partitions. So it's like they are not more than two partitions away from each other.
Two subdivisions. So yeah. So what you're trying to say is this: either they're both from the same subintervals. This is one possibility. The other possibility is that x is from here and y is from here. It cannot be that x is. It cannot be that x is here and y is in a subinterval which is not the next one or the previous one, but further away. Right?
Yes, sir.
Because if x is here, let's say, and y is here, then what you will get is y minus x would be strictly greater than xi plus 2 minus xi plus 1, which is greater than equal to delta. Just give me a moment, please. Sorry, yeah. So they cannot be, they have to be either from the same subinterval or from adjacent subintervals because of this. Okay. So if they're in the same subinterval, so one possibility is that x and y both belong to the same subinterval. So this is one possibility. In this case, by the theorem itself, the small span theorem immediately will tell you that this is less than epsilon by 2, and hence this is less than epsilon. The other case where they can be from adjacent ones, so in this case, what you can do is you write this as so x is from here and y is from here. You add and subtract f at this intermediate point. And now that same theorem and your choice of the partition will tell you that this is less than epsilon by 2 plus epsilon by 2, which is epsilon. So in either case, the difference fx minus fy is less than epsilon. So what you get as a corollary of the earlier theorem is that a continuous function defined on a closed bounded interval is uniformly continuous. Okay, so this is a corollary of the earlier result. Okay. Now, going back to continuity at a point. So, what are the different ways a function can fail to be continuous at a point A? So, if not defined at A at all, that is 1. 2, limit of fx as x goes to A does not exist, or at A, but they are not equal. So either the right hand side does not exist, which is 1 here, or the left hand side does not exist, which is number 2 here, or both sides exist but they are not equal. So those are different ways in which f can fail to be continuous. Okay, now suppose this exists and is finite. So this means that the limit is a real, not plus infinity or minus infinity. This exists. Then what you can do is you can define a new function, let's say, which is fx if x not equal to A. So except for A, at all other points, you define this function to be exactly equal to A, fx. And at A, what do? You define it to be this limit, exactly this number. So then about this function g, what can you say? Is it continuous at A?
Yes.
Yes. Because the limit of gx as x goes to A, that would depend on the values of g in a deleted neighborhood of A. But in a deleted neighborhood, that means as soon as you have left out the point A, g is exactly equal to f. So the limit would exist and would be the same as limit of fx as x goes to a. And then at this point, you have defined it so that that limit coincides with the value. So this g is continuous at a. So in terms of the original function f, then in such a case, you are able to remove the discontinuity at the point a just by redefining the function at that point. So such a point, such a discontinuity point is called removable discontinuity of f. So let's look at an example. So let's say okay, we'll look at 2 or 3 examples together, maybe. And at the point 0, you define to be something, let's say this. So let this be one first example. Second example. It's a minor modification of this first example. And then I'll come to a third example in a moment. So let's just look at these two first. So, and you'll be interested in at the point 0, what happens. So what is the, how does the function f behave near 0? So from the right, if you approach 0, what is the right hand limit as x goes to 0? So limit of fx as x goes to 0 from the right is plus infinity, right? And on the left of 0, the behavior is like this. So limit of fx as x goes to 0 from the left is minus infinity. So in this case, limit fx as x goes to 0 does not exist. So 0 is a discontinuity. So I mean, though it is, the function has been defined at 0, it does not matter. It cannot be continuous because the limit itself does not exist. Okay, what about this function? So here you have replaced x by mod x. That means the behavior would be basically symmetric around 0. On this side and on this side, there won't be any difference. It will be this. So here, x going to 0 would exist, but it would be plus infinity. So it exists, but it is not finite. So even here, it does not matter that f is defined at 0. It cannot be continuous because you have this limit plus infinity. So it cannot be equal to the value of f at any point. So both these examples, the point 0 is a discontinuity which is not removable. By just redefining at the point 0, you cannot do anything about its continuity because this limit, the behavior around the point will not change. Now let us look at this example. Gx is maybe I'll call this F1, F2, and F3. So this is F2, this is F1. So F3x is so you can simplify. So what is the definition? So for x not equal to 0, it would be 1 over mod x by 1 plus 1 over mod x, and x equal to 0, it would be half. So this expression, if you simplify this, what you will get is 1 plus mod x. So what about this limit? Does this have a limit as x goes to 0?
Yes.
Yes. So what is the limit?
1.
1. So whatever the behavior, it goes to 1, and it is symmetric also. So it would be both sides, it would look the same. I don't know how does it look, but at least it would go to 1, that much we know. But at 1, the value is half. So for this F3, you can see that you can just redefine. So you just change the definition of F3 0. Instead of half, you make it 1. Then F3 becomes continuous. So this function has a removable discontinuity at 0. Okay. So maybe I'll try and give a few exercises, few functions, and you can find out whether they have removable discontinuities or not. Okay, now so earlier I think I had mentioned that all these examples of functions that we had looked at, let's say x going to x to the power n, where n is a natural number, and then exponential x, okay, maybe then polynomial functions, which means that x going to finite combination of such things, x to the power some positive integer, not non-negative integer, and then exponential x and sin x and cos x, these functions. These are all continuous, right? Everywhere that we had observed already. Now I'll just mention two other important functions. I won't quite get into the proof in detail. So one is x going to, so one is a kind of extending this a little bit. So x to the power, x going to x to the power p, where p is a fixed positive real. Okay, now So what is the domain of this function? This is something, again, we did not get into detail, but I had mentioned this function, I think, at the beginning, how to define, etc. So we are interested in so as long as x is non-negative, you can define this. So that's one function, and the other function is p to the power x. So here again, p is something fixed, positive, real. So both these functions are continuous. So I'll okay. I said I won't get into the proof, but I'll just briefly indicate why. So let me start with this x going to p to the power x. Now this function, let's use a notation f. So f x plus y is, if you go back and look at the notes and look at how this was defined, and the properties also. So it has this property. So when you are trying to prove, let's say, okay, now trying to look at this quantity, you can write it as f x minus a plus a minus fa. This should give you f x minus a fa minus fa, which is f x minus a minus 1 fa. So basically, if you use this, then when you're trying to show continuity at a point A, you can reduce it to, so continuity at A can be reduced to statement about continuity at 0. In other words, and here also, okay. Now, suppose you are interested in this limit, and you want to show this. So what you can use for that is this statement, which is something I had, I think, stated as an exercise. And then so this may require a bit of work, and again, I mean, for the exam, I'm not going to ask anything about this function, but you should know that this function is continuous. That is what is that is something that you may need. Some other problem you need this fact, but actually proving continuity of this function, that you have to, you should spend some time, but for the purpose of the exam, you can forget it for now, the details, if you want. Okay, so now for this first function, what you can, x, okay. So that is also something continuous. So the statement that you will be looking to prove is this. So here, what you do is you try to prove this special case. So prove this special case. And then the general case would follow from that by observing that okay, so basically once you prove this, the other points it would follow. And how do you do this? Here you can look at the two limits separately. Now for this limit, what you are interested in are values on the right of 1, right? So that means you are essentially trying to prove this. So x is bigger than 1 in this case, so you write x as this, and the limit you are looking at is y going from 0 going to 0 from the right. So you are looking at this limit, and here you are looking at limit 1 minus y to the power p, y going to 0 from the right again. Okay, now try and see if you can handle these two limits separately. And once more, these limits that I'm talking about right now in the context of these two functions, these are kind of optional. So you can try this, but if your aim is just the exam, then you need not bother about it. But as I said, what we do need, meaning you will need, is are the facts that these two functions are continuous. So for example, let's look at one useful conclusion from using continuity of this second function. So what is the second function? Second function is x going to p to the power x. Okay, p is some fixed positive real. So now what we know is that, assuming this is true what I've stated, so this is continuous. Did I specify x here? No. So for the first function, it is this right hand side. for this second function, it is on the entire real line. Continuous on R, and f x plus y is fx fy. Okay, so sorry, what did I want to say? I an application. Okay, sorry. Maybe I'll come back to this a little later. So let me go back to the exponential function. I'll come back to this later. So let's go back to the exponential function once more. So exponential x was defined as the sum of this series. Now, what are the properties that we have seen so far of this exponential function? One, using product of series, we have seen exactly a similar property for this function. Then this is continuous on the entire real line. At 0, it is 1. Okay. Now let's look at a few more properties maybe. So I don't recall whether I mentioned this limit. So did we look at this limit? X going to infinity exponential x? No. Okay. So what do you think this limit is going to be? Any guess?
Infinity.
Plus infinity. So how to prove this? Any?
Show that a finite amount is not a limit.
But how to do that?
Show that is greater than
So
something
proof when we like bunched up a few terms. So like first we bunched up the second and third, then we fourth, fifth, sixth, or something like that.
Okay. So one way to do this would be just to focus on, see, we are interested in limit as x going to infinity. So we can restrict our attention to positive values of x. Because eventually we're interested in large values of x. So we can restrict our attention to x positive. And then if we look at the partial sums, they form an increasing sequence, right? If x is 0. And what is S1x? S1x is 1 plus x, right? And the subsequent partial sums are even bigger. So which means that right, you have this inequality. And then this would tell you that this limit is plus infinity. Is this okay, the argument?
Yeah.
Okay. Now, what about the limit x going to minus infinity? I mean, for this, if you look at the series, then there's a problem because the signs would alternate depending on whether you're looking at like n is even or odd. But there is a easier way because of this property. So which tells you that if x is positive, this is just 1 over exponential x. And this tells you that what does this tell you about this limit?
0.
0.
0. So we now know a little bit more about this function. This is plus infinity and this is 0. Okay, so let's see if we can compare exponential x and exponential y if x is less than y. Can we compare them?
It depends, I think.
Like, elaborate a little bit.
So let me. If both of them are negative, then it will be the reverse sign. Otherwise, so if both of them are positive, then it will be exponential x will be less than exponential y.
Okay, so if both of them are positive, then this would be the case. And you are saying that because
it's like the one upon exponential property only. Yes. Yeah.
So if this is positive, okay, so okay, I think what you are using is the following. If x is positive, exponential x is greater than 1. So that is another observation we can add to our list, right? That is relatively easy to see. If x is positive, then the first partial sum itself, 1 plus x, which would be greater than 1, and then the subsequent partial sums are even bigger. So you have this, okay. And so that would give you what you are saying here. Okay, now is it possible, so now question, can one have this for some x? So is this possible? Or, okay, let me write another question.
No, sir. It shouldn't be possible.
Okay, so why?
Sir, because suppose it is for say some point x. Then we
Let's
take
say
another point y which is less than x. Then we do a similar thing. No. So obviously it's not possible for any positive point because of the
positive point, they're in fact greater than 1 value.
Yeah.
Yes.
So let's suppose x is a negative point.
Okay. Okay.
Yeah. So we know that 0 is greater than a. So exponential x into exponential.
Go ahead.
That's what I'm thinking.
So exponential x into exponential minus x will be 1.
Right.
And
So if this point is negative, a is negative, then you just use this. So now minus a is positive, so this is something positive. The product is 1 positive, so this has to be also positive. Right? You have shown that the function is on the right side of 0, it stays above 0, positive. And for any point here, you just look at the values at these 2 points. Their product is positive, and the value at this point is positive. So the value here also would be positive. Right? So in fact, exponential x is positive for all x because of that. Right?
Yes, sir.
Okay. So it is always positive. And so going back, so this is not an issue. Both for any x and y, the values at those 2 points are positive. So, and now you use the fact that whenever y minus x is positive, this is greater than 1. That means you get exponential y by multiplying this with something greater than 1. So this is bigger. So it's increasing. So is increasing. In fact, if you look at the proof, it is strictly increasing. Okay, now let us try to find the exact range of this function. So what is your guess? What is the range?
1 to plus infinity. No, 0 also possible. So 0 to plus infinity.
0 to plus infinity. Okay, now on the left of 0, should it be a round bracket? Should it be a closed bracket?
Round bracket.
A round bracket. So range of this is this. Okay, now we have to prove it. So how do we prove this?
Since like the limit of limit of exponential x if x goes to minus infinity is 0.
Okay.
I mean, like if we decrease x more and more, exponential x will tend towards 0, but will never reach it. So
okay.
and same with like plus infinity.
Yeah, but we also have to show that no point is missed. Every point in this interval that is in the range, that is also something you have to show, right?
Yeah.
So how do we do that?
use intermediate value theorem.
Right. So what we want to show is that we take some c between 0 and infinity. So that is some positive real. We want to show that there is a point A where it takes this value. Okay. So now here is how you can show this. So first, let us maybe instead of exponential x, I'll write fx because I have to write less. So f now is just exponential. So x going to minus infinity is 0. Okay. So there is a real, whatever you call it. So let's say n such that x less than n implies fx less than c. This is fine.
Yeah.
I'm just using this statement, limit of fx as x goes to minus infinity is 0. Here c is something positive, so there would exist capital N such that this happens. So let's look at capital N minus 1. So capital N minus 1 is going to be less than c. The value is something less than c. And next you use the fact that x going to plus infinity is plus infinity. So that means there would exist a m such that x greater than m would imply fx greater than c. Right? Again, you can do this. This is just using this fact that the limit is plus infinity. So now from this, you take, let's say, m plus 1 and n, let's say, just so that this quantity is bigger than n minus 1. So if you take this, then so what should I call it? Maybe z. At fz, it would take a value which is bigger than fc. And at n minus 1, it has a value which is less than c. Now over this interval, this is it. You apply intermediate value theorem. C lies between these two values. So there is a point where it would take the value C. Intermediate value theorem. So is this fine, the proof?
Yes, sir.
Okay. So now what we know is that range of, okay, now I'll get back to writing expression, is the entire positive real line. Okay, now, so this function goes from R to here. Is it an injective function? Is it a bijective function? So injectivity means what should we have?
Strictly increasing.
So strictly increasing will give you this. Because between x and y, there are only three options: x less than y, x equal to y, x greater than y. But when inequality happens, because it's strictly increasing, fx and fy cannot be equal. So injectivity will get as a corollary to that. So it's injective. And what we just now showed is that this is the entire range. That means it is onto. So it is in fact a bijection from R to this. So there's an inverse function going from 0 to plus infinity to R. So this inverse is what we call the logarithm. So exponential goes from R to 0 to infinity, and logarithm goes from here to R. So log of exponential x is x for all x in R. Exponential of log of x is x for all x in 0 to plus infinity. Okay, now I'll just, what time is it? Okay, so I'll write this as a very general kind of statement. So see what all properties of logarithm you can derive from properties of the exponential function, and exploiting the fact that this is the inverse function. I mean, in particular, for example, let's say for exponential, we know this. Okay, so what does it tell you about the inverse function? So let's call this Z, let's call this W.
Sir, it says that log of ZW is log of Z plus log of.
Right, so X is what? X is log of Z. Right, if Z is exponential X, log is the inverse function, that means log of Z would be X. So X is nothing but log of Z. Similarly, Y is nothing but log of W. So you get this property for the inverse function. This property means the property and also about its other properties, like what happens to whether it's increasing, decreasing, whether you can say anything about it. Then what is the limit as x goes to plus infinity? What is the limit as x goes to minus infinity? Is it continuous? Okay, so just one thing I had missed completely while discussing limit and continuity, etc. So let me just quickly do that. So suppose you have two functions, f. So right now, let's not worry about their domain range, etc. So f is a function from R to R, and g is another function from R to R. Okay, suppose limit of fx as x goes to a is c. And let's say limit of gx as x goes to, or maybe I'll use a different limit of gy as y goes to c is d. Assume this. Now, suppose you are looking at the composition, which is G composed with F. This is the notation, G small circle followed by F, or sometimes you just like write G of F of this. So question, so if F goes to a limit as x goes to a, and that limit is c, and then G goes to Gy as Y goes to C is D. Will the limit of the composition be D?
Yes.
Okay, why?
So we'll choose some epsilon neighborhood around D, and
Just a moment. Epsilon neighborhood of D.
and since limit
Okay.
of the function G is D, there will be and a delta neighborhood around C. And since then limit of f of
Okay, so first you are using the second limit, right? So let's call
Yes,
it
sir.
1 and let's call it 2. Okay, so let's see. So this is where you start. So use 2 is what you're suggesting. So there is a delta positive such that, okay, such that what happens now? Y minus C
less than delta,
less than delta
implies G of Y minus G of C.
not G of C.
Sorry, minus D is less than epsilon.
Okay, just look at this statement carefully. Any modification needed here? Right, this is a limit. So you are not interested in the value at C, but only in values of G at points close to C, right?
Okay.
You exclude the point C. Okay, now go ahead.
Now for this delta, using 1,
okay,
there exists some delta 1 greater than 0, such that 0 less than x minus a implies f of minus c. Yeah.
Okay, now we'll try to combine these two, right?
Yes, sir.
Now the problem now would be precisely because of this. See, when you take x close to a, x within delta 1 distance of a, fx should be within delta distance of c. Okay,
Yeah.
but you don't know whether this should be fx should be different from c.
Okay.
And because of that, you won't be able to use this statement, this implication.
Okay, sir.
Okay, okay. So think of, for example, f could be a constant function. Right. F could be just the constant function c.
Okay.
Yeah. So then what would happen is, for the composition, you would actually be looking at just g of c. Okay. And that will not tell you anything about the limit of right?
So then the composition function will be a constant function.
Sir, if we say that suppose limit fx extends to a c and limit y tends to c, gy is equal to d, and g is continuous, then will that work?
Say it again.
So everything the same plus
Right.
that g is continuous, then it should
Right.
work.
So that I'm going to come to just in a moment. So as far as the limit is concerned, there's a problem. Okay, maybe what I said is if we take the constant function, then that's not quite the right thing. But okay. First of all, this argument there would be a problem, right? That part is clear. That because from here you can conclude this, but this says nothing about this being positive, so that you cannot conclude this. So now let's try to get a counter example where this is C. So what can give us a yeah?
So let's take fx to be 1 by x and a to be infinity. So c will be 0.
A to be plus infinity. Okay.
And then c will
Right.
be 0. And then define gy to be equal to gy to be equal to gy to be equal to y, except at 0 it is equal to 2, something like
Gy to be, sorry,
gy to be equal to
0.
y,
Sorry, just a moment.
yeah,
Gy to be equal to 1 if
x is equal to 0. Sorry, y is equal to 0.
uh-huh.
And gy is equal to y for all else. So then like if for d equal to 0.
So here y going to 0 is
But
0.
But y is not equal to
And right, and limit fx as x going to plus infinity is 0. But when you look at the composition, G composed with F, that is so what is that? X not equal to 0, 1 over x. And now we are trying to get plus infinity of this, which is which is 0. So what do we have to look at if we try to construct a counterexample? Maybe so what, again, just go back to the argument. Where is the problem here?
if
Will
fx
we
is
need
equal-
FA to be equal to C?
But here we are concerned about limit. So FA need not be equal to C, right? I mean, just
I mean, to get the counter example, yeah.
so okay, what I was saying initially. So let's say f is a constant function. Let's say 1. And then let's say g is this. So what I want is, let's say something like this. So gx is x minus 1 if x not equal to 1, and let's see. So limit fx as x goes to 0, let's say this is 1. Limit gx as x goes to 1. This limit is 0.
Yeah.
And g of f, the composition is, what is the composition function? This is 1, right? The constant function.
Yes.
Yes. So if you look at this limit, that is going to be 1, which is not this number. See here, f being a constant function, the composition would depend on just the value of g at this point. It will not give you any information about the value of g in the neighboring points. But this number, the other number, the d, limit of gx as x goes to c is d. That d is based on the behavior of g at the surrounding points. But in such a case where f is a constant function, g of f will be independent of the behavior of g at the surrounding points.
Yes, sir.
Yeah. So that's why you get that's how you get a counterexample here. Okay, so now you can just go back to the statement and see. So this is something I think I'm way over time, so maybe I'll just stop. So instead of just these two limits, if you have continuity of f at a and continuity of g at c, then you will have, so this answer is no, but f continuous at a and g continuous at fa, these two would give you g composed with f continuous at a. So just check this. So you can either go through this epsilon delta route. So basically the same argument would work, because when continuity, I mean, when talking about continuity, this restriction goes away. So exactly this argument would be applicable there for continuity. And the other way to argue would be in terms of sequences. So you can check this. So for continuity, composition of two functions, continuous functions would be continuous. As far as limits are concerned, you have to be careful because of precisely this reason. Okay, so let me stop here. And I brought it up because that I'll start with next time. Exponential of logarithm of x is x. So the composition is the identity function. Similarly, logarithm of exponential of x is x. The composition is identity function there. So with that we can do something like what will this tell us in that context? So anyway, so let me stop here today. Any questions or comments? Okay, so if not, let me disconnect and see you next week.
Thank you, sir.
Okay.